What if you could plug your STM32 into a computer and have it show up just like a USB drive? You could copy files to it, delete them, and manage them just like any normal external storage device. No complicated setup, no extra chips needed. In this video, we are going to do exactly that using the USB Mass Storage class on the STM32. Hello and welcome to ControllersTech. This is the fourth video in the STM32 USB series. In the previous videos, we covered how to set up the STM32 in USB device mode. In this video, we will continue using the STM32 in USB device mode, and today we will talk about the USB Mass Storage class. So basically, when the STM32 is connected to a computer, the USB Mass Storage class makes the STM32 behave as if a storage device is connected to the computer. It will show up as an external drive, just like a USB flash drive or an external hard disk. In this video, I am going to connect an SD card to the STM32, and then using the USB Mass Storage class, that SD card will be read as an external drive by the computer. This means you can copy files, paste files, delete files, and do all the usual operations you would do on any external drive. And the best part is, you do not need to write any file system code for the SD card on the STM32 side. The Mass Storage class handles all of that for you. For this video, I am using the STM32F446 development board from React Studio. This board already has a built-in slot for the SD card. That slot uses the SDIO interface pins on the STM32, and I am going to use the same interface in this video. Here is the schematic of the board, and here you can see exactly which pins are connected for the SDIO mode SD card interface. Now, along with the SD card demo, I will also show you how you can use the internal RAM of the STM32 as a small storage device. This will just be for demonstration purposes, to show that the same USB Mass Storage class can work with different types of storage. So a part of the available RAM on the board can be used as storage that shows up on the computer. We will get to that in a while. Let's start by opening STM32CubeMX to create a new project. As I mentioned, I am using the STM32F446RE microcontroller. Let's start with the clock configuration. The React Studio board I am using has an external crystal on it. So I am enabling the external high-speed crystal to provide the system clock. The board has an 8 MHz crystal. We will use the PLL to bring the system clock up to the maximum possible speed, which is 180 MHz for this microcontroller. Now go to the Sys tab and enable the serial wire debug option. This allows us to flash and debug the board using the debugger. I have already covered how to configure USB in the previous videos of this series, so I will skip most of the explanation here. We are still using the USB in device mode, and the USB runs at 12 megabits per second, which is the full-speed USB standard. The pins PA11 and PA12 are configured as the USB data pins, and this matches the schematic of the board. Now go to Middleware, then USB Device, and enable the Mass Storage class. I have already explained most of the parameters in a previous video. Now there is one new parameter here called the Media Packet Buffer Size. Let me explain what this means. When the computer talks to a storage device over USB, it does not read or write 1 byte at a time. Instead, it reads and writes data in fixed-size chunks. These chunks are called sectors. For SD cards and most flash storage devices, the sector size is 512 bytes. This is a standard that has been used for a very long time in storage devices. So every time the computer asks to read or write data, it will always ask for at least 512 bytes at a time. The media packet buffer size tells the USB Mass Storage class how big that buffer should be, so it can hold exactly one sector of data while it is being transferred. If you set it to anything less than 512 bytes, The data transfer will not work correctly because the buffer would be too small to hold one full sector. So we keep it at 512 bytes to match the sector size of the SD card. Now, since we are connecting an external device like an SD card, it is a good idea to also enable serial logging. If something does not work correctly, the log messages will help us figure out what went wrong. So I am using UART1 for the logging purpose. Enable UART1 in asynchronous mode and leave the settings at their default values. The pins PA9 and PA10 are selected as the UART transmit and receive pins. Here is how I have connected a USB to TTL adapter to read the log data on the computer. The TX pin from the STM32 is connected to the RX pin of the USB to TTL module. We only need data to flow from the STM32 to the computer, so we only need this one connection. That is all the configuration needed for now. We will add the SD card configuration later in the video. For the first part, I am only going to enable the RAM as the storage, so we do not need the SD card just yet. Now if you look at the clock configuration, you will notice there is an issue. The USB peripheral is not receiving exactly the 48 MHz clock that it needs. We need to adjust the PLL settings, so that the USB peripheral receives exactly 48 MHz. Alright, the clock issue has been fixed now. Let's go to the Project Manager tab and give a name to our project. Also make sure to select STM32CubeIDE as the toolchain, then click Generate Code to generate the project files. The project has been generated, so let's now import it into STM32CubeIDE. Alright, the project has been imported successfully, and here we have our main file. Before we start implementing the USB part, let's first make sure our serial logging is working correctly. Here we will create a new custom write function. This function routes printf data through UART1, so any printf call in our code will send its output to the computer via the USB to TTL adapter. If you are using a different UART on your board, make sure to change the UART handle right here in this function, and everything else will work the same way. Next, include the standard I/O header at the top. This is needed so that the printf function is available in our code. Now inside the infinite loop, we will add a simple printf call to print a short string, and then add a 1-second delay after it. This way, the string will print once every second, and we can confirm on the serial console that the logging is working. Let's build the project and flash it to the board. Also open your serial console application on the computer. Make sure the baud rate and other settings in the serial console match exactly what we set for the UART1 peripheral back in CubeMX. Let's connect the board, and as you can see, the string is printing every 1 second. That confirms our serial logging is working correctly, and we are ready to move forward. Now we will start writing the USB-related code. But before that, let's quickly look at the build analyzer. As you can see, this board has a total of 128 kilobytes of RAM, and out of that, around 122 kilobytes is currently free. Since we have so much free RAM available, we can take 100 kilobytes of it and use it as a storage area. This storage area will then be exposed to the computer as a drive through the USB Mass Storage class. Again, this is just for demonstration purposes to show that the Mass Storage class is working before we bring in the SD card. Now, the files related to USB storage are located inside the USB device folder in the project. Out of all the files in that folder, we are only interested in one file, USB device storage if.c. This is the file that acts as a bridge between the USB Mass Storage class and the actual storage, whether that is RAM, an SD card, or anything else. We will write all of our storage-related code inside this file. So let's go through the functions available in this file one by one, understand what each one does, and then modify them to fit our needs. The first function we have is storage init. This function is meant to initialize the storage before it is used. Since we are using RAM as our storage, we do not need to do any initialization. RAM is ready to use as soon as the board powers up, so we can leave this function as it is. Next is the storage get capacity function. This function is called by the computer when it wants to know the size of the connected storage device. We need to modify this function to tell the computer how much storage we have. This function has two parameters. The first is the block size, and the second is the number of blocks. Together, these two values define the total storage capacity. The block size should match what we set in STM32CubeMX, which is the media packet buffer size of 512 bytes. So we will set the block size to 512 here as well. The number of blocks depends on how much memory we want to use as storage. Since we are using 100 kilobytes of RAM, we need to divide the total memory by the block size to get the number of blocks. 100 kilobytes is 102,400 bytes, and dividing that by 512 gives us 200 blocks. However, the value we enter here needs to be one less than the actual number, so we will enter 199. This is just how the USB Mass Storage protocol counts blocks, starting from 0. We will also add a printf here to print the block count and block size on the serial console. This way, when the computer connects and asks for the storage capacity, we can confirm in the logs that this function was actually called. The next function is storage is ready. This function is called by the computer to check if the storage is ready to be accessed. Since we are using RAM, it is always ready. So we just return a success value here and move on. After that is storage is write protected. This function tells the computer whether the storage is read only or not. We want to be able to write to our storage, so we return not write protected here and leave it as it is. Now we come to the two most important functions, which are storage read and storage write. These are the core functions where the actual data transfer happens. But before we write these functions, let's first define a buffer that will act as our actual storage. This is a simple byte array of 100 kilobytes that sits in the RAM of the STM32. All the data that the computer reads from or writes to our storage device will go through this buffer. Now inside the storage read function, we will call the memcopy function to copy data from our defined buffer to the data buffer that the USB stack provides. The block address parameter tells us which block the computer wants to read. We multiply the block address by 512 to convert it from a block number to a byte offset inside our buffer, because each block is 512 bytes in size. The block length parameter tells us how many blocks the computer wants to read in one request. We also multiply this by 512 to convert it to the number of bytes to copy. The storage write function works the same way but in reverse. This time we copy data from the USB data buffer into our defined buffer. So whatever the computer writes to the storage gets saved into our RAM buffer, and when the computer reads it back, it gets the same data from that buffer. That is all the code we need to write for the RAM storage demo. Let's remove the test printf from the main loop since we no longer need it, and build the project. Now if you look at the build analyzer, you can see the RAM usage has gone up to around 105 kilobytes. This makes sense because we defined a 100 kilobyte buffer inside the RAM, and the rest is used by the stack and other variables. Let's flash this project to the board and open the serial console. Right now nothing is being printed. Now when I connect the USB cable to the computer, you can see the capacity log appearing on the serial console. This confirms that the storage get capacity function was called by the operating system as soon as the USB was connected. You can also see that the computer has detected a new external storage device. However, right now this device does not have any file system on it. It is just raw memory with no formatting. That is why the computer is showing a prompt asking us to initialize or format the drive before using it. So let's go ahead and format the drive to create a new file system on it. If you are on a Mac, make sure you select the master boot record partition scheme along with the FAT file system when formatting. This is important because some operating systems default to a different partition scheme which may not be recognized correctly. Alright, the formatting is done. Now we have a new external drive showing up, and it has around 47 kilobytes of free storage available. The total capacity is a little less than the 100 kilobytes we defined because some space is used by the file system itself after formatting. Now let's try storing a file on it. Here you can see the drive is showing up in the File Explorer as an external drive, just like any normal USB storage device. Let's copy a small file onto it. I am going to use a system file that is around 27 kilobytes in size. Let's copy it and paste it into the drive. And there we go. The file has been successfully copied to the external drive, which is actually just the RAM of our STM32 acting as storage. Now let's do a quick test to confirm that the data stays in the RAM as long as the board has power. I am going to disconnect the USB cable while keeping the power connected to the board through the SD link. This means the STM32 is still powered on and the RAM still holds its data. Now when I connect the USB cable again, you can see the storage get capacity function was called again in the serial console. And if you look at the drive in the File Explorer, our file is still there. This confirms that as long as the board has power, the data stays in the RAM and remains accessible. However, this will not always be the case. Let me show you why. Now I will disconnect both the USB cable and the SD link, so the board completely loses power. When power is lost, the contents of the RAM are erased immediately. Now when I power the board back up and connect the USB again, you can see the computer is asking us to initialize the drive again. The file we copied earlier is gone. This is because RAM is volatile memory, which means it only holds data as long as it has power. The moment power is removed, everything stored in the RAM is lost. So RAM cannot really be used as a permanent storage device. The reason I showed this demo is just to prove that the USB Mass Storage class itself is working correctly, and that any storage medium can be connected to it, whether it is RAM, an SD card, or a flash chip. The USB Mass Storage class does not care what the storage is underneath, as long as the read and write functions are implemented correctly. Now let's move on to the actual use case. We will replace the RAM storage with a real SD card, so the data is stored permanently and survives power loss. Let's go back to STM32CubeMX where we need to configure the SDIO peripheral for the SD card. Go to the SDIO peripheral and enable it in 4 bits wide bus mode. The 4-bit mode means the SD card will use 4 data lines at the same time to transfer data, which gives us 4 times the speed compared to the 1-bit mode. After enabling it, you will see that some pins are automatically assigned, but they may not match the actual pin connections on our board. So we need to reconfigure the SDIO pins according to the schematic of the React Studio board. Let me go ahead and reassign the pins to the correct ones as shown in the schematic. Alright, the pins are now configured correctly. Next, let's look at the clock settings for the SDIO peripheral. You can see that the SDIO peripheral is currently receiving a 48 MHz input clock. The actual clock that goes to the SD card is derived from this input clock using a divider. By default the clock divider factor is set to 0. If we put 0 into the formula, we get a 24 MHz clock for the SD card. This is the maximum clock speed we can provide to the SD card using this peripheral, and it is perfectly fine for our use case. So we will leave the divider factor at 0. Just to show you how the divider works, if you change the divider factor to 1, the formula gives us 16 MHz. So increasing the divider factor reduces the SD card clock. You can use this if your SD card has trouble working at higher speeds. But for now, I will keep it at the default value of 0 to get the full 24 MHz. Also make sure to enable the hardware flow control option. This helps prevent data overflow during transfers by making the SDIO peripheral signal when it is ready to send or receive data. Leave all the other parameters at their default values. That is all we need to configure for the SD card. Now click the Generate Code button to regenerate the project with the new SDIO configuration, and let's go back to STM32CubeIDE. Now, if you look at the SDIO initialization function that CubeMX has generated, you will notice something important. During the initialization, the bus width is set to 1-bit mode first. Then, after the initialization is complete, it is switched to 4 bits wide bus mode. This is the correct way to initialize the SDIO peripheral. The SD card needs to start communication in 1-bit mode, and only after the initialization handshake is done, can it be switched to the faster 4-bit mode. If CubeMX has not done this automatically for your board, you will need to do it manually. Now let's go back to the USB device storage if.c file. This is where we will write the code for the SD card. Let me first comment out the 100 KB RAM buffer we created earlier, since we are no longer using RAM as the storage. This frees up that memory so it can be used for other things. Now let's go to the main file. Here you can see the SD card handler variable that CubeMX has generated. We need to use this same handler inside our USB storage file. So let's copy the variable name and declare it as an external variable at the top of this file. Now let's go through each function and update it for the SD card. Starting with storage init, the SDIO peripheral is already initialized by the generated code in the main file, so we do not need to do anything extra here. Next is storage get capacity. Here we need to read the actual capacity of the SD card, and use that to fill in the block count and block size parameters. So let's create a structure of type SD card info type. Then we will call SDGetCardInfo function, and pass it the SD handler and this structure. This function reads all the card information from the SD card and stores it in that structure. After that, we update the block size and block count parameters using the values stored in the card info structure. And just like we did in the RAM demo, we will also print these values on the serial console so we can confirm that this function is being called by the operating system when the USB is connected. Next is storage is ready. Here we cannot just always return ready, because the SD card may be busy doing a transfer. So we need to actually check the current state of the SD card. We do this by calling SDGetCardState function, and checking if the card is in the transfer state. The transfer state means the card is idle and ready to accept a new read or write request. If the card is in any other state, we return not ready. This prevents the USB stack from sending a request to the SD card while it is still busy. For storage is write protected, we leave it returning not write protected, same as before. Now for the most important part, the storage read function. Here we call SD read blocks to read data from the SD card. We pass it the SD handler, the data buffer, the block address, the number of blocks to read, and a timeout value. We will set the timeout to the maximum value to make sure it does not time out during a large read operation. Now there is something important to understand here. Even after SD read blocks function returns, it does not mean the SD card has finished transferring the data. The function returns before the transfer is fully complete. So we cannot return from the storage read function until the data is actually ready in the buffer. This is why we wait in a loop and keep checking the SD card state until it goes back to the transfer state, which confirms the data is ready. We will also add a printf to log that this function is being called. However, we cannot print every single time this function is called, because the SD card read and write operations happen very frequently, and adding a print every time would cause delays that could make the transfer fail. So instead, we will only print every 1000 times the function is called. We check if the block address is a multiple of 1000, and only then we print the address to the serial console. The storage write function follows the exact same logic, but instead of read blocks we call write blocks. Everything else stays the same. In the print statement, we just change the label to write, so we can tell in the logs whether it was a read or a write operation. Alright, that is all the code we need. Let's build the project. No errors, so we are good to go. Before we flash the project, we need to make sure the SD card is formatted with the FAT32 file system. So let me insert the SD card into a card reader and connect it to the computer. Here you can see the SD card in the disk utility. It is a 16 GB card. Let's format it with the FAT32 file system, and give it the name SD card. The formatting is done. The SD card now has a FAT32 file system on it. I am also going to copy a couple of files onto the SD card right now, so that later when we connect it through the STM32, we can verify that those files are still there and the data is intact. I have now inserted the SD card into the STM32 development board. Let's flash the project to the board and then open the serial console to view the logs. I have not connected the USB cable yet. Let me connect it now and see what happens. As soon as the USB is connected, you can see the Sprige Get Capacity log appear at the top of the serial console, showing the number of blocks and the block size of the SD card. Right after that, you can see multiple read addresses being printed, which means the storage read function is being called repeatedly by the operating system. This is normal. When the computer first detects a storage device, it reads various parts of it to understand the file system, check the partition table, and load the directory structure. Once all that initial reading is done, the SD card shows up as an external drive on the computer. And as you can see, the files we copied onto the SD card earlier are still there and intact. The data has been preserved correctly. Now if I delete those files, you can see the write logs appearing on the serial console. This confirms that the storage write function is being called by the operating system, when a write operation takes place on the drive. If you right-click the drive and check its information, you can see the total capacity matches what we saw earlier in the disk utility when we formatted the card. Now let me try copying a larger file to really test the read and write performance. I am going to zip up an STM32 project folder. The resulting file is around 16 megabytes. Let's copy that to the SD card and watch the logs. As the file is being copied, you can see the write logs printing rapidly on the serial console, confirming that data is being written to the SD card block by block. Once the file copy is complete, the operating system reads the data back to verify it, and you can see the read logs appearing now as well. Everything is working exactly as expected. We are successfully using the SD card as an external drive through the STM32 USB Mass Storage class. So that is all for this video. I hope you understood how to use the STM32 USB Mass Storage class to make an SD card show up as an external drive on your computer. We also saw how the same class can be used with the internal RAM as a quick way to test things before connecting the actual SD card. In the next video of this series, we will use the W25QSBI flash memory chip as the external storage. If you are looking to use an SBI-based SD card instead, you can follow the same logic from the next video, since both use the SBI interface to read and write data. That is it for this video. I hope everything was clear and easy to follow. You can download the complete project from the article linked in the description below. If you have any questions or run into any issues, feel free to leave a comment. Keep watching, and have a great day ahead.